There's a database that logs every lightning strike on Earth down to millisecond level precision. So I wanted to know, could I locate where a video was taken using just the background thunder sounds? Because if so, this could be genuinely useful for things like or any other cases where there's just very little visual information. The low frequencies of thunder travel really far and they penetrate structures extremely well. Also, because most of the thunder sound sits in that low frequency, it's often inaudible if you're just casually listening. But then if you look at the audio in a spectrogram, it's almost like an invisible fingerprint. So that's the goal. The basic idea is that with the location and time of each strike, we can model what that would have sounded like at every location, and then just compare each one versus the audio. We also wouldn't know when the audio was filmed, so for each point, we'd have to compare every time frame as well. But in theory, that exact cadence of strikes should be localized to a pretty specific area. We need two things for this. One is some audio of a thunderstorm, and two is all of the lightning data. The hardest part of this project was actually getting geolocated, time-stamped footage of a thunderstorm. If you just look up thunderstorm audio, you're just inundated with these AI videos trying to get that 8-hour sleeping ad revenue. I found a couple real ones, even some that I could geolocate. However, the date of filming wasn't clear. And for context, this will be a proof of concept. So we'll build this with some audio that we know the location and date of, but we'll build the pipeline blind to both of those facts. That way we can verify the accuracy of the result, but it's not influenced by knowing the location. So rather than looking for thunderstorm audio that I could geolocate and timestamp, I just shifted to live streams that I could easily geolocate and then just wait for a thunderstorm. The problem is that most live streams like this don't actually have audio. The one category I found that did consistently was these bird feeder cams. So now I just need to get a list of these that I know the location of and just wait for lightning. And this actually leads me to the other input we need, which is the lightning data itself. So on this site, pulling historical data is abysmal. So I'll go to random date, here are all the strikes, and you can see the location of the strike along with the exact time. However, the way this data is fed to the browser is actually just static image tiles. Like, let me pull one up here. Okay, so like here's this one. It's genuinely just a square image with X and Y coordinates attached. So to pull this, I would need to query all of these images and then restitch them, run OCR to extract the text, and then detect the position of each of these dots to log where the strike was. I actually did that and it was a huge pain, but still, there are instances like this where these strikes overlap and you just simply can't get that data. Like here are the closest 3 zoom levels. This one which has no data, zoom in 1, overlapped, and then one more overlapped again. So like aside from just being a huge pain, this would also cause my data to have gaps in it. But now if I go to the live view, this actually shows strikes popping up in real time. That tells me actual data is being fed to the browser rather than those static tiles. So if I just go into DevTools and refresh, there should be something like a socket or other live data connection that's feeding that. So going past these PNGs, looking for that, we can see a WebSocket here. And then under messages, each strike containing the lat, long, time, and then a bunch of other data. So this is the live data feed we need. Then I just used Python to emulate what a browser would send so that we could listen in on that socket and just log every strike. I didn't want to do that on my computer nonstop, so I just set up a free AWS server that logged every lightning strike on Earth 24/7. It also had a process running where if any strike was detected within some radius of one of the bird feeder cams, it would then go to that link and start recording that bird feeder. Saying that all out loud sounds a little bit absurd, but after doing that for a couple days, I had the audio and the corresponding strike data. So now we can start matching. So how will this actually work? Well, the lightning data contains the position and the exact time of the strike. So for an observer at any given location, I can model what they would have heard and then compare that versus what we hear in the audio and score based on the similarity. So on the modeled audio, this is where it does get a bit technical, but I'm going to try to make it all understandable. So let's take just one strike, this green one here. We need to model 2 things. One is the time that the strike would be heard, and 2 is the amplitude or loudness that it would be heard at. On the timing, we can just use the distance times some speed of sound constant. However, just using the horizontal distance won't work because lightning's sound source is not right at the ground. For the cloud to ground strikes or CG strikes, that's what this data set primarily covers, that acoustic source is about 2 kilometers high. So the time delay to get to a listener is actually the slant distance here. That doesn't seem like much, but I mean, in this example, it's a 2.5 second difference of when you would expect to hear that strike. You can also model wind and other atmospheric conditions, but it's a pretty minor effect, so I just assumed the 343 meter per second constant here. So that's the arrival time. The second component is the loudness. Now, loudness is a bit simpler with one caveat. The closer you are, the louder it is, and as you get further away, it follows an inverse square decay. As you get super close, the modeled loudness is ridiculously high. So high that a YouTube bird cam microphone wouldn't capture 180 decibels. It would just clip. So the one caveat is I just set a cap on that exponential growth as the strikes get extremely close. So you can see here's what this curve would look like for actual data. So that's the modeled curve. Now for what we actually match it to. I got this audio from one of the live streams in Central Florida, and you can see each of the lightning strikes here. Now we can't just match the modeled curve to a spectrogram, we have to create a similar curve from this spectrogram. Lightning energy, like you can see here, is primarily in the 20 to 250 hertz range. So I just ran a bandpass filter and then measured the RMS at each point to get this blue line. You'd need to be careful about wind noise though, because that peaks the same frequencies as lightning does. However, I picked live streams that had pretty sheltered mics, so I didn't have to worry about that. So we've covered both curves, the modeled and the observed. Now for how we actually match them. There's one more important step that I didn't cover here, and that's normalization. It's a YouTube live stream, so it's not giving us the raw absolute decibels. The important info here is actually relative loudness between these strikes. So that's the other thing this blue curve does, is it normalizes relative to the loudest strike it heard. Now we want to build this blind to the exact time of recording. If we knew the exact time, it'd become a lot easier, but also a lot less useful. That means for each location, we need to do a time sweep at whatever delta t increment over whatever window we want to look at. Said another way, we test what if this audio was recorded at exactly 3 p.m. at exactly this location? What would it sound like? And then we do that again, but for 3 p.m. and 5 seconds later. So at each step, we take our normalized observed audio and compare it to the normalized modeled audio. The crucial distinction here though, the modeled audio needs to be normalized within whatever time window we're looking at. All of the strikes in our observed audio are normalized relative to the loudest one heard in this window. The audio clip has no idea what happened before or after it. So the modeled audio needs to also only be normalized with the strikes in that window. And then the last step is we just smooth both of these curves a little bit. If you don't, it looks like this. So smoothing helps if we have a genuinely good candidate, but the delta t increment just misses that alignment perfectly. It also allows us to not have to run as granular delta t increments and a bit coarser spatial resolution on the initial pass as well. And then the last step is how do we determine mathematically how similar two curves are? To do that, we use something called cosine similarity. I won't go into the details, I'll give you the 20-second version of what this means. At each point in time, you multiply the two values. Since the observed curve stays the same across all candidates, that just means a louder, noisier modeled location would score higher. That's where the next step comes in. You divide that numerator by a factor that includes the total modeled energy. Meaning, yes, the numerator is high for something that's super loud, but then the net score is brought down by that total modeled energy. So the highest scoring curve would be the one that's exactly loud enough at exactly the right times. We're going to run this under the prior that we know the day that this was recorded, but not the time, and we know nothing about the location. So we're scanning the entire world. So that audio clip we have is from July 2nd. Here are all the strikes that occurred on July 2nd. So we'll lay a grid of points at 5-kilometer resolution across the entire Earth. Then we'll keep only the ones that meet a couple criteria. The first one, our audio is about 30 minutes long and it has like 15-ish strikes. So we'll require that a point has at least 10 strikes within a 30-minute window. That's one criteria. The second is that the point is on land, although this would actually work for a video taken out at sea. So after doing that, here are the remaining points. There's about 90,000 in total. But remember, at each point, we need to do that time sweep for the whole day at 5-second increments. That's about 8,000 checks per point times 90,000 points. In total, about 700 million checks. That's where using cosine similarity here comes in handy a lot, because we can use a fast Fourier transform, or FFT. Now this isn't a math channel, so don't worry, I'm not going to go into detail. Just know that FFT is an algorithm that makes it extremely efficient to calculate these cosine similarity scores across multiple time offsets. So that's the entire methodology. Let's look at the scores for each of these points. We know the location is in Central Florida, but the pipeline does not. So let's look at these points. So cosine similarity puts out a score between 0 and 1, 1 being the best, and I colored higher numbers, hotter colors here. So like in China here, we have a couple decent ones around the yellow-orange range at 0.64. That's just kind of to give you a scale as we scroll through. Everything else down here is pretty cold colors, roughly neutral in North Africa, Europe, a couple oranges again. Moving over to the US, roughly same, until we get down to Central Florida here. Now I'll show you the actual curves that it matched for 3 points. I'll do the highest scoring and then kind of a mid score and then just random noise. Here's the highest scoring one. It has pretty good alignment with these first 4, although the amplitude isn't perfect. It also has this random false positive in the data, but overall pretty well aligned, and it scored first by a decent margin. Here's a histogram of the scores for every point, and I colored the ones within 25 kilometers of the actual location in red. The reason you can't see them is because they're all the way over here by themselves at 0.78. So this is great separation. Here's the mid-scoring one. So there's some more timing misalignments here. Amplitudes are a bit off, but overall it's still got the same storm. And then here's just the random noise point. If you note the time here, it actually scored low enough on the real storm that it just found a better scoring time elsewhere. So it probably had this large peak here, and then the delta T sweep just aligned that and then took the points. So even with a lot of these imperfections, the actual location still scored a lot higher than just random noise. So using only a 30-minute clip of background thunder sounds, we're able to get not even just the country or the state, but the city that it was filmed in. And that's not all though. I ran that same analysis again, but on just this area with finer grid resolution and smaller delta T increments. And here's the result. So now it's not even just city. This can tell you the likely neighborhoods within that city. Now I told you the audio is from Central Florida. I didn't tell you where exactly. I'm not going to dox these old people's bird feeder cam. What I will tell you is the best scoring point was within 5 kilometers of the real location. I also did one more run that I think is a more realistic use case. So say we know the general area, but we don't know the exact day that it was filmed on. That's what this does. I think I captured the lightning data for like 3-ish weeks. So basically every point in Florida gets struck by lightning every month. But I ran the same analysis for that longer time horizon, and here are the results of that. Very similar. So that's great. It proves that it scales both spatially and for longer time uncertainty. Now you'd probably think that this level of precision from background audio alone is already insane. I would agree with you. However, as I was doing this, I noticed another type of clue that blows this out of the water. The precision goes from a few likely neighborhoods to basically, this is the house that you recorded it in, still entirely from background audio. However, that deserves a video of its own. Now lastly, there were a few important things to note on all of this. The free Blitzortung data that I used has 2 major limitations. First is that it primarily captures cloud to ground strikes, or CG strikes. The second is that the location deviation for each strike, I think, is around like 1 to 5 kilometers. So in terms of seconds, that's like 3 to 15 second plus or minus delay. That means this type of storm was on the easier side to locate. It was primarily cloud to ground strikes, and it had good separation between each strike. That's just a limitation of the free data I had available. There are, however, much better paid data sources. To the degree of, rather than a 5 kilometer deviation, you're down to like 100 meter precision. And that enables 2 things actually. One is just your location estimate for a single strike is a lot more precise. The second though is it allows you to analyze all different types of storms. The problem we had here is the poor spatial precision creates an attribution problem. Like if the strikes are too close together, the location uncertainty makes it such that we don't know which modeled strike to attribute to each heard strike. With 100 meter precision, you know exactly. That also means you could probably do what we did with a 30-minute clip with like a 5-minute clip of just dense thunder. If anyone watching this has access to that data, you work in meteorology or something, I would love to try it. So shoot me a message on Discord if you want to send it over. But I mean, this is what we were able to do with free open source data and still narrow it down to about a 5 kilometer area. So in short, do I think your location is leaked if you have thunder in the background of your video? With a bit of effort, someone could probably know your city depending on how long the video is. With a few $1,000s for commercial data, they could do a bit better. However, I wouldn't worry about thunder because all of this pales in comparison to the other audio clue I found. So I'll see you in a future video for that.